You've seen it before, right? That frustrating secure connection failed error? It just pops up and stops you dead in your tracks. But what is actually going on under the hood? Well, today we're going to put on our detective hats and crack the case of the failed SSL/TLS handshake. So, what does that SSL handshake failed message really mean? I can tell you it's not just some random glitch. Think of it like this. We've just been called to the scene of a digital crime, and our first job as investigators, well, it's to figure out why this connection failed in the first place. At its very core, an SSL handshake failure is a breakdown of trust. Seriously, think of it like two spies meeting up. They have a secret handshake, right? A specific sequence to prove they are who they say they are. If one of them gets it wrong, boom. Trust is broken, the meeting is off, and no secrets get exchanged. That is exactly what's happening between your browser and the website server. Okay, so to solve this whole mystery, we've got to understand how trust even works on the web. And it's not magic, believe me. It's actually a really carefully built hierarchy, something we call the chain of trust. And pretty much every single secure connection you make depends on this chain being absolutely 100% intact. So, where does it all begin? Well, it starts at the very top with the Root Certificate Authority, or CA. You can think of it as the godfather of internet trust. Its certificate is self-signed and it comes pre-installed. It's already baked right into your browser and your operating system. And the private key for this root? Oh man, it's one of the most protected secrets on the entire planet. We're talking offline, physically secure hardware, and it lasts for like 20 or 30 years. This is the ultimate anchor of trust. But you wouldn't send the Godfather out for everyday jobs, right? That's way too risky. So instead, the root CAs sign certificates for what we call intermediate CAs. These are the public-facing workhorses. They're online, and their whole job is to issue certificates to web servers. They're a super important security buffer, because if an intermediate gets compromised, the root of trust, the Godfather, is still safe and sound. And that brings us to the final piece, the leaf certificate. This is the one that's actually installed on the web server you're trying to connect to. It's signed by one of those intermediate CAs, and its only job is to prove the identity of that specific server. It's the end of the line, the leaf on the tree of trust, and it can't be used to sign anything else. Okay, so how does your browser actually check all this? It's pretty cool. First, it gets the server's leaf certificate. Then, it looks at the signature on that certificate to see which intermediate CA signed it. Next, it looks at the signature on the intermediate certificate and follows that all the way back to the root CA. And since that root CA is already in your browser's built-in trust store, boom, the whole chain checks out and the connection is trusted. And this right here is exactly why that whole hierarchy is so important. Look at the impact. If a single website's private key gets stolen, well, that's bad. But the severity is pretty low. You can revoke it and replace it in a few hours. Now, what if an intermediate CA gets compromised? That's a medium-level disaster. You'd have to revoke every single certificate it ever issued. But what if a root CA gets compromised? That is catastrophic. We're talking the entire foundation of internet trust for millions of people just gone. It would literally take years to recover from something like that. All right, now that we understand this whole chain of trust thing, we can get back to our investigation. Let's head back to the crime scene and start looking for clues. The problem could be on your end, the client side, or it could be on the server's end. Let's start with the easy stuff, the client side. And you would be absolutely amazed how often the culprit is just an incorrect system clock on your computer. I'm serious. Certificates have very strict start and end dates, so if your clock is off by a day, perfectly valid certificates can look expired. Other simple things to check, maybe your browser cache is holding on to an old, bad version of the cert, or maybe your browser is just ancient and doesn't support modern protocols like TLS 1.3. Heck, sometimes it's even your own antivirus software getting in the way and messing with the connection. Okay, so if everything on the client side looks good, our investigation moves to the server, and let me tell you, the #1 most common problem here is a simple server misconfiguration. The server sends its leaf certificate, but the admin forgot to include the intermediate certificate. Without it, your browser can't complete that chain of trust we just talked about. Other big suspects? A protocol mismatch. The server is trying to use an old, insecure protocol like TLS 1.1 that your browser flat out refuses to use. Or they can't agree on an encryption algorithm. That's a cipher suite mismatch. It could even be something called an SNI misconfiguration, where a server hosting multiple websites on a single IP address just sends the wrong certificate for the site you're trying to reach. As a security engineer, when you dig into the server logs, these error codes are your bread and butter. They're the clues. See an unknown cat error? That's your smoking gun for a missing intermediate certificate, almost every time. Certificate expired? Well, that one's pretty self-explanatory. Handshake failure, cipher, tells you they couldn't agree on how to encrypt the data. And then there's certificate required, which points to something a little more advanced.
Right. So up to this point, we've only talked about a one-way street. Your browser, the client, is verifying the server. But what if the server needs to verify you? What happens when the server needs to be 100% sure about who the client is? Well, that's where we get into the world of mutual TLS, or mTLS.
Think of it this way. Standard TLS is a one-way street of trust. Your browser checks out the website. Simple. But mTLS, that's a two-way street. Your browser verifies the server, and then the server turns around and demands a certificate from your client to prove its identity. You're not going to see this on public websites, but it is absolutely essential for locking down communication between back-end services, like APIs and microservices. But mTLS, as you can imagine, adds a whole new layer of complexity. Suddenly, you're not just managing one certificate for your server, you have to manage a certificate for every single client. That means issuing them, renewing them, and revoking them for potentially thousands of clients. It adds a performance hit, it can cause compatibility headaches. It's incredibly powerful, for sure, but managing it is a massive operational challenge. Okay, so we've investigated the crime scene, we've identified the main suspects, but a good engineer doesn't just run around fixing problems after they happen. They build systems to prevent them. So the real question is, how do we stop these handshake failures from happening in the first place? Well, the whole industry is moving towards shorter and shorter lifespans for certificates. We're talking going from years down to just a couple of months, or even less. This idea is called crypto agility, and it's great for security because it limits the window of opportunity if a key ever gets stolen. But when certificates expire that fast, trying to renew them by hand is just impossible. You can't do it. The only way to survive is through automation. A really solid automated certificate management system does four main things. First, it has to be able to discover every single certificate on your network. You can't protect what you don't know you have. Second, it has to automate the whole issuance and renewal process, so certs never expire. Third, if a certificate gets compromised, you need to be able to revoke it instantly. And finally, a good system uses open standards like Acme. That's the protocol behind Let's Encrypt, so you're not locked into one vendor forever. Let's dive into a really common practical problem that automation helps solve. Imagine you have a Java microservice, and it needs to securely talk to two other microservices. But here's the catch. Each of those services requires a different client certificate for mTLS. How can one application juggle multiple identities like that? It's a classic Java challenge. The elegant solution here is to build a kind of dynamic certificate selector. So instead of having a static config that just points to one single certificate, your application uses a custom key manager that holds a map of all its different certificates. Then, during the handshake, this manager is smart. It looks at the server it's trying to connect to and says, for this server, I need to present this certificate. This allows a single application to dynamically and securely talk to all those different mTLS endpoints without a fuss. So if there's one thing you walk away with today, I hope it's this. A secure connection isn't just a bunch of code running. It's a story. It's a story about trust built one link at a time, all the way from that super secure root CA down to the web server. And the handshake fails when any part of that story falls apart, when a link in the chain is missing or a character in the story simply can't be trusted. So now you know how to be the detective. You have the tools to diagnose why a handshake failed. But the real challenge, the next level challenge, isn't just about fixing the last problem. It's about engineering your systems so the next one never even happens. So I'll leave you with this question. How are you going to automate your infrastructure to manage all this trust at scale? That's the real mystery to solve. Thanks for joining this explainer.